All right, well, greetings, and this is a lesson that I want to go through with you, even though I don't think you need a lot of guidance. I just want to make sure that you're understanding that we can solve vector problems not just with scale diagrams, but we can do it more exactly by doing some calculations that we already know how to do. So I'm going to help you fill in these examples, and then you'll have a chance to finish some practice questions in the near future. If you consider this problem, we have an airplane that's traveling at 200 kilometers per hour, and the wind is from the west, so it's going east. We're going to figure out how fast the plane is going. So in terms of a vector, anyways, if we talk about this being the wind going to the east, if the plane is also going east, we would add the two of them together. And clearly then the answer would be 250 kilometers per hour, because you would add the wind to the speed of the airplane and they would be equal. If the airplane is going west, though, we would find if we draw that first vector again going east at 50, the one going west, and I'll just draw it a little bit underneath, will go back. Well, how much back will it go? Because our resultant vector from where we start to where we finish will be the difference between the two of them. So 200 subtracted from 50 or vice versa means we actually end up going 150 kilometers per hour, but in a different direction. This time we would end up going west because the speed of the airplane is greater than the speed of the wind. You're slowed down, but you're still going west. So there we don't need to do any calculating. Here, when we talk about going north, here's where we can use our Pythagoras' theorem to find an answer. So we're going north now, the wind is still going to the east, and our resultant vector is there. So let's go ahead and label our vectors with their measurements. Notice I didn't worry about any sort of scale, and the reason is we're not solving by scale, we're solving by calculation. That doesn't mean I don't use a straight edge, it doesn't mean I don't put arrows on my graph, it doesn't mean I don't label my diagram, it just means that I'm not worried about it being to scale. So applying Pythagoras' theorem, and this is something that you can show if you want. I am confident that in grade 12 you can do Pythagoras' theorem without showing a whole bunch of work. But if you need to, go ahead. I know some of you like to put your thoughts on paper, and that's great. Some of you will like to just do it, get the answer, and write that answer down. So I got 206.16 kilometers per hour. That is going to be the value of our resultant vector, which is over here. So some of you just might label that after you calculate it without showing any work, and as I said, I am completely fine with that. I know in grade 9 you can do Pythagoras' theorem. I'm trusting you can do it now. The second part, though, is the direction, and we always take the direction from the tail of the resultant vector, which is where we started, which would be right there. I'm using the Greek letter theta. To find the value of that, please use non-rounded answers. This R vector is a rounded answer, so any of the trig functions, sine and cosine, that use the hypotenuse we're not going to use. We're going to use tangent because that will get us a more exact answer, because 200 kilometers per hour and 50 are not rounded. So we're going to use the second function button, 200 divided by 50, and then we're a second function tan that. And I got 76 degrees. Make sure your calculator is on degrees if you're not getting that same answer. We'll round to the nearest degree. We will not worry about going to any decimal places. In the last scenario, 50 kilometers per hour to the east and then north 40 degrees east creates a problem that we could not use sine, cosine, and tan for, at least not in the basic trig ratios, because it's no longer a right triangle. In order for us to solve for that, you have two options. One is to use the cosine law, which you might remember as a squared equals b squared plus c squared minus 2bc times the cosine of the angle. But we're not going to worry about that for now, because a little bit later on we're going to talk about resolution of vectors, which also could allow you to do that question. And we'll also talk about that again next week. An example problem, we've got a swimmer. This is one that I've talked about in class. So a swimmer's going across the river at a certain speed, but there's a current taking that person downstream, and we want to see what the actual path is, and then how long would it take, and then how far off would that swimmer be. So I like to draw a diagram for these problems so I can picture what's really going on. So correct me if I'm wrong, but the swimmer is going from south to north. So the swimmer wants to go in this direction. The fastest they can swim is 1.8 meters per second. The river is going current to the east, and so that would be at 1 meter per second. The actual path the swimmer will take, again assuming that they continue to swim at that same speed, would be at the angle as follows. So without reading a heck of a lot into the question, I'm going to go ahead and find the value of that using Pythagoras' theorem. So 1 squared plus 1.8 squared. Yes, I used my calculator for 1 squared. I am still waking up this morning. Square rooting that, I got 2.06 meters per second. And to find the measure of that angle, I would like you to write this part down, the tan part, even though many of you will do it without error. There are some who will do it with error, and I need to see why, so I can help you figure that out. So make sure you're showing your work on the angle calculation, please. I got 29 degrees. Now let's look at the questions. Let's find the swimmer's resultant velocity relative to the riverbank. So the resultant velocity is a vector quantity, which is your resultant vector. So 2.06 meters per second, and then the direction would be north, 29 degrees east. Done. How long it will take to reach the far shore? We're looking for the time. Well, we have to know the distance in order to find time, and we're told earlier in the question that the width of the river, at least at this point, is 200 meters. When you look at the vectors, you automatically would be led to maybe use the r vector, but that vector is taking you not only across the river but downstream. In order to find how long it would take you to go across, we would use the value that is taking us across, which is 1.8. Because even though we're going at an angle at 2.06, really we're still only going across the river at 1.8 meter per second. So when I go to calculate the time, so speed is distance over time, so therefore time is distance over speed. Our distance is 200 meters, and that would be to the north. Speed is only 1.8 meters per second because that is also the speed going north. Notice the north will cancel out if you're looking at it mathematically. Time does not have a direction, it is a scalar quantity, and I'm getting 111.11 seconds. Now, how far downstream? Similarly, if we look at the diagram, well, how fast are we going downstream? Well, now we use this blue vector, the one going downstream, which is 1 meter per second. And the distance downstream is speed times time. Notice every time I use a formula, I'm writing it down. Again, that's so you can communicate with me that you know what you're doing. 1 times 111, we still get the same answer because the speed is 1 meter per second. 111 meters, and that would be downstream, so it's east. This is a vector quantity, so let's put a vector symbol or an arrow over top of the D. So that's part of what you're going to do today, is use those calculations to solve problems. I'm going to leave this example and the next example, or the next question, maybe for next week if we need to go through it. In the meantime, though, I'd like to talk to you about resolution of vectors. It's, again, nothing that's going to be too complicated for you, but you need to understand it to do all of your assignment. The basic logic is there are infinitely many vectors that I could draw to get the r vector, which I'm going to highlight in yellow. I have a purple set of vectors that would work. I could also start here, go way over to here, and then come back to here. Well, that's still going to get you the same r vector. And here, right there, we're going to end up at the same place. Next week, I think we're going to do our lab as vector golf, and we're going to see the same thing, that you're going to try and go from the tee box to the hole, which is like the start of this vector and the end of that vector. And there's many different ways to get there, depending on your shot that you take in golf. What we're going to focus on, though, is only 2 vectors. And the 2 vectors that we're going to focus on are the horizontal or vertical components of the vector. So I'm going to draw this one. It's going west 47 degrees north, so somewhere here. And that is a northwest vector or a west-north vector. So that means that I can split it up into 2 parts. One vector that's going west, and then one that's going north, and that creates a 90-degree triangle. We're told the angle is 47 degrees to the north of west, and that the value is 26, we can find the horizontal component, which we're going to label with X, and we can find the vertical component, which I'll note as Y, and that's just sticking with the math terms because we're familiar with those as being vertical and horizontal already. And we're going to use sine or cosine to figure out those values. For instance, if I want to find the value of Y, the sine of 47 degrees would be Y over 26 kilometers per hour. And when you calculate that, you'll get your north vector. So please do that right now. If you haven't grabbed your calculator yet, I will do the same. And hopefully we all get the same answer. I got 19.02 kilometers per hour. Please make sure you put the direction with it as well, which is north. To find the value of X, we would use cosine. And the same calculation will get you the correct answer. Notice I didn't use tan. And again, the reason I didn't use tan, even though we already had the Y value, and we could have used tan, is that our answer would not be as accurate because our 19.02 is a rounded answer. We want to use our exact number of 26 so that our answers are as accurate as possible. And that vector would be going west. Make sure you have I guess you should put a vector symbol over the X and Y as well. So that's pretty much it. I've gone through it fairly quickly. I recognize that, and you may have some questions on that next week, and I'm okay with that. During class today, you are expected to get done, first of all, the first 6 question on the vibrant vivacious vectors assignment, if you haven't yet. Then you're doing assignment number 2. You can have the answers up, and I'll just go ahead and grab those for you actually right now. If we go to my physics files, go to kinematics, and go to assignments, and we want to go to assignment number 2 answers. No. And you'll have these here. You can just pause the video and put them up, or you can go back and find the file and open that up. Otherwise, I'm done. You'll have a great day today and a great weekend. Stay safe, don't do anything silly, and I'll see you, God willing, on Monday.